These are the lesson 7.4 notes on equations in two variables. Up till now, in chapter 7, the beginning of the chapter is on solving equations, and you've just had one variable in there. And the second half of the chapter, 7.5 through 7.7, is on solving inequalities. Those are problems that have a greater than or a less than in them, and they will also only have one variable. But there's this little section in the middle, 7.4, that has equations with two variables in it. The two variables are x and y, and they are written as an ordered pair so that you can graph them. So this is the little tiny algebra section about graphing equations that's getting you ready for more graphing in 7th and 8th grade, all right? So some of these words should be familiar from STEM or from science. Some new vocabulary in math is that the independent variable is a variable that's free to change, and we are going to graph that on the x-axis. So I'm going to do a little picture to go along with that, where I have like my coordinate plane with my x-axis, and the y is the vertical axis. And so the independent variable, the thing that can change, is graphed here on x. And on the y-axis, we graph the dependent variable. The dependent variable depends on the independent variable. Okay, so if you think about being independent in your life, it means that you're free to make choices, or you're free to make it to some extent. You can do what you want. The independent variable is the one that is free to change, all right? And then the dependent one, the one that we put on the y-axis, depends on whatever the x variable is. And that will make more sense as we go along. So we've got 3 examples. The first example is about ice cream. And you say that ice cream costs $3 a scoop. If you go somewhere like Lord's or Cold Stone, they charge you maybe by the scoop, or sometimes it's the size of the scoop. But we're going to keep it really simple for our problem. We're not even going to put any toppings on there, okay? So when I want to find out how much I have to spend for my ice cream, the cost is equal to $3 times the number of scoops. So first I'm kind of writing it in words so I can think about the problem and make sure I understand, and then I'm going to turn it into an algebraic equation. So I know that my cost depends on the number of scoops. The cost, which is your y value, depends on the number of scoops that I buy. So I'm going to change the cost into y equals 3 times the number of scoops, that's my x value. And now I have an equation in 2 variables. It's an equation that has 2 variables in it, an x and a y. Okay? And now I'm going to use a table of values to help generate some ordered pairs, and then I will use the ordered pairs to make a graph. So the first x value that I'm going to use, the x is to stand for the number of scoops, and the y stands for the cost. So I'm going to do it for 3 scoops, and 4 scoops, and 5 scoops. So if I had 3 scoops and I substitute 3 back here, I get 3 times 3. Maybe I'll write that over to the side. 3 times 3 is equal to 9. And if I got 4 scoops, I would have 3 times 4, that's 12. And if I got 5 scoops, hopefully that's for more than one person. 3 times 5 is 15. And then I make an ordered pair that has the x value and the y value paired together. 3, 9. 4, 12, and 5, 15. Okay. All right, and now I can take these values and I can graph them. So I'm going to make my y-axis and my x-axis. And I know that x stands for the number of scoops, and the y is the cost in dollars. And I just look at my numbers to see what I should count by. So I see that my x values are just going up by 1, and those are small numbers, so I should be okay numbering by ones. Notice when you're numbering that you are numbering a line, not a space. Okay, that's important because when I graph, I want to put my dot on top of a line, and if you put the number over here in the space, then I don't know where to put my dot. All right, so number lines. And then when I look at my y values, they're bigger and they're counting by threes. And I think that it would be easy to number my y values by threes. I could try numbering by ones. I could try numbering by twos, but I think threes are going to fit well with these numbers. This point is 0, 0, so you can't put a 3 there. You have to start numbering at that line. 3, 6, 9, 12, 15, and that's as far as this data goes, but you could keep counting if you want to, right? And then I graph the ordered pair 3, 9. So I'm going to go over to 3, the x, and then go up the amount of the y, which is 9, and put a dot right there on the lattice point. Then I'll graph 4, 12. Go over 4 and up to 12 and put a dot, and then over 5 and up to 15 and put a dot. And hopefully everybody still has their ruler. If you've got a nice clear ruler, then it's easy to line them up. And I see that this line is actually going to go right through 0, which makes sense because if I didn't order any scoops of ice cream, then my cost should be 0, right? So 0, 0 is a point that makes sense on this graph, right? Then we want to check and see if I extend this line out, will the point 10, 30 be on the graph? You could check by counting over to 10, 6, 7, 8, 9, 10, and then going up and seeing if that point is 30. Is that point 10, 30? And I believe that it is. You can also check by taking your equation, y equals 3x, and you substitute 10 and 30 in. Y is this value. They're in alphabetical order. So the first one is x and the second one is y. So put 30 in for y and 10 in for x. And then I have 30 is equal to 30. So yes, that's a solution. So everything goes together. If you take a point on this line, it should make this equation true. You can check to see that that a solution is true by substituting it in, and it will be an equals. Everything that is a solution, anything that will make this true, will also be on this line. And anything that is on this line will also make this true. And there are no extra points off of the line that would make that true. The equation and the line go together. They're different ways of showing the same information. One's a picture and one's an equation, but they're the same. Okay, then for example 2, we are looking at ages. Okay. And so we have you are 3 years older than your sister. And for this problem, we're going to say that your age is equal to your sister's age You're 3 years older, so you have to take her age and add 3 to get your age. All right, and then we're going to change that into an equation. So I can see here that my age, y, depends on my sister's age, x. My age is the y, or your age, y, is equal to the sister's age, which was x, plus 3. So in this example, we have an addition problem. In the other example, we had a multiplication problem. Okay. And we're going to choose some values here. I think in class we chose 9. Different classes might have different numbers here. That's okay. And so if if the sister is 9, then my age, 9 plus 3, would be 12. At point 0, when sister is born, so she's 0 years old, I am 3. And let's pick a point in between, like 5. When the sister is 5 years old, I'm 3 years older, so I am 8. Okay, and then we make those into ordered pairs, 9, 12, 0, 3. That's a really important point that we'll get to in just a minute, and 5, 8. Okay, and then we're going to graph those from the table. So draw your y-axis and your x-axis. And we know that in this problem, we decided to make the sister's age be the independent variable, and my age, or your age, depends on what the sister's age is. And how should we count? Let's see, it looks like these numbers, the independent numbers are pretty small, and I can count by ones. Okay, and then the y values are a little bit bigger, and a nice number doesn't jump out at me. I'm going to count by 2s. Remember that you're counting by the line, and you're not counting, there's that 0 point. You start counting at the next line. 2, 4, 6, 8, 10, 12. I think that's high enough, isn't it? Okay. And then we can plot our points and go over on the x to 9 and then up to 12. And put a dot. And over to 0 and up to 3. And I don't have a 3 written on my graph, but I know that 3 is halfway between 2 and 4. So put it right there on the y-axis. And 5, 8, over to 5, and up to 8. And if we have plotted our points correctly, they should make a nice straight line. Right? And we'll notice that this time it doesn't go through 0. Last time it went through 0, but this time it doesn't. So we'll talk about what's different about this. First, let's check and see if the point 27, 30 would be on the graph. That means that if I extended this out, if I go in all the way over to 27, would my graph be at 30? It might even be further out. Would 2730 be on the graph? Well, we can check by writing our equation, y equals x plus 3. And I know that the first value is the x, and second is the y because they're in alphabetical order. So I can substitute in 30 for the y value and 27 for the x value. And then I have 30 equals 30. And yes, that is a solution. So that means that when my sister is 27, I'm 30. And yes, I know that that's true. I'm 3 years older than her. So even after years and years go by and she's 27 years old, I'm still going to be 3 years older than she is. We're going to add 2 more new words and look at how they are tied to the graph. The y-intercept is the starting point. That's where the graph crosses the y-axis. When you are graphing equations in algebra, this is a super important part of the graph. And this problem is right there. The y-intercept is 3, right? The point where it crosses. And then think about what that means. What does it mean when, let's see, this is my age is 3. What is happening when my age is 3? Oh, my sister's age is 0 because that is when your sister is born. So 3 is your age when your sister is born. So her age is 0 and your age is 3, right? It's important when you are graphing equations to show where it crosses the y-axis. This y-intercept is an important point. All right, and then we have the idea of a slope. The slope tells you how much the graph is going up. And I can look at that. I think we should look at that from a T-chart, which I can do it right here. If I look at how much my x value is changing from here to here, if I go from 0 to 9, that is going up 9. And from 3 to 12 is also going up 9. And so if I have, I'll write it as, I'll write it like this. When we're finding the slope, we write the change in the y value, and we put that over the change in the x value. You'll do this a whole lot in 8th grade. Okay, but if I look at this y value, I can see that it is changing by 9. And the x value is also changing by 9. And if I simplify that, that simplifies down to 1. And that kind of makes sense. It should make a lot of sense if we think about it in the context of the problem, that every time your sister, she's the X, every time she gets 1 year older, you also get 1 year older. The time is passing at the same rate for you and for your sister. If you picked a different point to look at, if we did this one like from 0 to 5, that one's going up by 5. And if we go from 3 to 8, that is also going up by 5. So if you had picked a different point, 5 over 5, that also equals 1. So the slope stays the same through the whole problem. So any 2 points that you pick should always give you the same answer. This slope is going up by 1, goes up by 1 because for every year that you get older, your sister gets the same amount older. Or I should have said that the opposite direction. Every time she gets older, you also get older by the same amount. Okay. And then we have a problem with dog walking. I'm going to kind of put 2 things together now. So if you are a dog walker, you charge a base rate to come to the person's house and to get their dogs, get everybody leashed up and ready to go. And that base rate is $10. So we're going to say that the price that you charge them is $10 plus, if they have more than one dog, you are going to charge them $8 times the number of dogs. So if they have 2 dogs, you would have to have 8 times 2, and then you would add on the 10. If they have 3 dogs, you would do 3 times 8, and then add on the 10. Okay, so then let's change that into an equation where the price depends on the number of dogs. So you have the price, so that's the y, and that is equal to 10 plus 8, and the number of dogs is this x. So there's our equation, all right? And the independent is the dogs, and the dependent is the price. So let's just choose some numbers. I'm going to choose 3. So if I walk 3 dogs, then to find out how much that costs, it's $10 plus 3 dogs times 8. And so that's 3 times 8 is 24, plus 10 is 34. Remember that you are allowed to use a calculator, or you can practice your math, get your skills strong. Okay, for 4, still charge the base of rate for $10. Now I've got 4 dogs, and each of them costs $8. 4 times 8 is 32, plus 10 more is 42. And then I'm going to write something crazy on there. What if have you ever seen those movies and they have the dog walker in the city and they have all the dogs together? Okay, imagine you've got 8 dogs that you're walking together. Base rate of $10 plus 8 dogs times $8. 8 times 8 is 64, plus 10 is 74. Okay. And ordered pairs, 3, 34, 4, 42, and 8, 74. Okay. And then a thing about graphing is that you always have to kind of figure out what scale to use on your graph, because it is not always practical to count by ones, right? I don't want to count by ones up to 74. That's silly. Going across the bottom, see this X value, that's my dogs. Always label your axis so we know what goes there. And I know that the Y is the price, and that's money. It's dollars. Okay, and I can see that these numbers are pretty small, and I should be able to go up by ones. Remember to make it on the line, not on the space. And for my price, I'm going to count by tens, and that could make it a little funny to graph, but it'll be okay. We're going to graph by 10. Might have been able to go by 5s. 30, 40, 50, 60, 70. No, 5s wouldn't have fit on there because I have to go all the way up to 70. I have to get to 74, so 5s wouldn't have worked. Okay. So then let's put some points on the graph. Over 3 and up 34. Over 3, up 10, 20, 30. Here's 35 in the middle, so 34 will be a little bit under that. Over 4 and up 42. 10, 20, 30, 40, a little bit above that, and 8 and 74. So I've got 8, and here's 70, there's 75, so it's going to be just a little bit less than half. And use your straight edge. Hopefully you have a nice clear ruler. Okay. This line flip up. Looks pretty good. All right. So far, so good. And then we'll check and see if 658 is a solution. What does this mean? That means, would 6 dogs cost $58? Let's see. So the equation that we're using is y equals 10 plus 8x. We will substitute in 58 for the y. And 8 times 6. 6 times 8 is 48, plus 10 is 58. So yes, this one was a solution too. Sometimes they are not on the line. Should have given you one that was not a solution. So if we extended this out, oh, in fact, that's this point right here, right? If you do 6, I'm switch to a different color pen. Over to 6, up to here, should be 58. It looks like it's 60 here, but it should be really close to the line, unless I made a mistake. 8 times 6 is 6 times 8 is 48, 50. Yep, 58. All right. So now we're going to get really algebraic, getting pretty mathy with this. Are you ready? Let's look at the y-intercept and what that means. The y-intercept is the place where it crosses the y-axis. That's right here. The y-intercept. It's crossing right there at 10. What does that mean? Where's the 10 in the problem? The 10 is right here, right? It's the starting. It's the starting, like, base rate. Okay? So the y-intercept is kind of the starting point. It's the base rate. In this case, it was that constant that was sitting there by itself. In all of the problems, we had a 10, right? A constant of 10. And that 10 turned into the y-intercept. That's a really powerful thing to know. Right? The slope is how much so it's going to be is the change in the y over the change in the x. So let's do that from our table. When our x value, this is going up by 1, right? Let's see. How much did this go up? If I go from 34 to 42, that's going up by 8. So the change in the y, it has to go on first, is 8, and the x is changing by 1. I've got another point in here. Let's check the other point. This time, my x value went up by 4. So I've got another point here that is 4. And from 42 to 74, I might have to grab my calculator and see 74 minus 42. No, I can do that in my head. 4 minus 2 is 3. No, it's not. 4 minus 2 is 2. And 7 minus 4 is 3. So this is 32. Oh, look at, I wrote them backwards. This who? I wrote that backwards. 32 is on top. The y value has to go first. So you have 32, and the x is 4. And look at that. 32 over 4 is the same as 8 over 1. So no matter where you are in the chart, it will still simplify down to the same slope because this line has the same steepness, the same slope all the way through. It's straight. You can connect the dots. And that's because anything in the chart will simplify down to the same number, right? So what does that mean? Where is the 8 and where is the 1? Oh, the y is the cost, right? Or the price. And the x is the dogs. So this is the price for one dog. The slope is a rate. The slope tells you like how fast something is going or how much something is changing. And in this case, it's telling you how much the price is changing for every dog that you add on. So slope is also super important stuff. Okay, this is a long set of notes, so it's okay to separate it out. After that first set of notes, there should be a big ideas assignment. So after example 3, there's a big ideas assignment that goes with that much. And then the second chunk of the notes is about the distance formula. So the distance formula is a special equation in 2 variables. Still has 2 variables. It has rate and time. It has distance. This is the y value, and the time is the x value. Okay, so this is called the distance formula. The distance is equal to the rate times the time. If you think about that, you know that your rate is how fast you're going. So say you're driving your car at 60 miles an hour, and then when you want to figure out how far you've gone, well, you have to multiply it by how long you've been driving. So how fast you're going times how long you drive gives you how far you went. Right? Let's connect this back to our x and y. So this d, notice that it's the only one that's capitalized. The d, that's the dependent. How far you go depends on how fast you were driving or how long you were driving. Dependent. Okay, and that's the y value. And then the t is the independent. And here's a little thing. If you have time in a problem, time is almost always the independent variable because you can't really change time. Time is usually just passing, and it's almost always the independent variable. And so that's going to be on the x-axis. And that, the rate, is the slope. The rate equals the slope. And that's a powerful thing to know too, that all slopes are rates. A slope is a rate. Right? Okay, so we have 2 examples that go with this one. We have driving 60 miles per hour. There is our distance formula. Distance equals rate times time. Right? So I'm going to change that into an equation with variables in it. So I'm going to put in d is equal to, what was my rate? My rate is 60 miles per hour. So I'm going to put 60 in for the rate. And the time is just going to stay t. Okay, so there's the equation. This is like y equals 60x. So it still has 2 variables in it. All right. So the distance depends on the time. Let's substitute in some numbers. And the numbers we're going to use are 1 and 2 and 5. So when I substitute in my distance, is going to be equal to 60 times 1. So that's going to be 60. Here, D is equal to 60 times 2. 60 times 2 is 120. And here, distance, if I go 60 miles an hour for 5 hours, I will go 300 miles. It's a long way. Okay, let's write some ordered pairs. So your x is 1 in 1 hour. I can go 60 miles. In 2 hours, I go 120 miles. And in 5 hours, I'll go 300 miles. Okay. So now let's do our graph. There's the y. There's the x. Label x is time. And in this case, time was in hours. And the y value is the distance. In this case, it is miles. And let's decide what units to use. Bump this up a little bit. Okay. My time numbers are pretty small, so we should count by ones. And my x numbers are pretty big, going up to 300. I think that actually 60 is a nice number to use. It'll graph nicely because they're going up. Be sure that you start at the first line, not at the 0. 60, 120, 180, 240. Is that right? Yep, 300. All right, 6, 12, 18, 24, 30. We'll put one more on there. 360. Okay, and then we can plot those points. Over 1 up 60, over 2 up 120, over 5 up to 300, drawing a line. Should it go through 0? If you've driven for 0 hours, should you go 0 miles? Yes, it makes sense that this line would go through 0, 0. Right. And then just pulling back together, so the y-intercept on this one is 0, because at 0 hours you would not have driven any miles at all. So there's the y-intercept. And then pulling back together the idea that the slope is a rate. It's a rate in miles per hour. We know from the problem that that should be 60. We're driving 60 miles per hour. Let's look at what that looks like on the graph here. If I make this and this, you'll do this in 7th or 8th grade also, kind of make this little triangle. So we can look at how much is this y going up. If it's going from 120 up to 300, or from 120 up to 300, that is 180, I believe. So this is 180. That's the change in the y value. You went 180 miles. And the x is going from 2 to 5. So the change from 2 to 5 is 3. So I'm going 180 miles in 3 hours, a change of 180 and 3. And if I simplify that fraction, 3 goes into 180 60 times. So I have 60 miles per hour. And that's my rate. Okay. All slopes are rates. A slope will always be a rate. And there's one more problem, and we're not even, one problem with 2 parts, but we aren't going to graph it. We don't have to make the table this time. You have homework problems in big ideas that look like this. So I wanted to be sure I gave you a good example. So now you are writing an equation in 2 variables that shows the relationship between the time and the distance. Right? So we're going to use that distance formula to write an equation that looks like this. Right? And so when I look at this problem, I see 10 meters in 2 hours. So I know that probably easiest to think about the x. No, let's don't do it like that. Sorry. That's going to be confusing. Okay, so the rate, which is also the same as the slope, because the slope is a rate, the rate is 10 meters per 2 hours. Think about that. The rate that whatever this is moving is 10 meters in 2 hours. So I write that as 10 meters per 2 hours. And then I need to simplify. So you need to change that fraction. 2 will go into 10 5 times. So I've got 5 meters per 1 hour. In the next chapters, we'll look at this. This is a unit rate. So I've got 10 meters in 2 hours. I've got 5 meters in 1 hour. Okay, so here's my rate. So when I want to write it as D equals RT, I take the distance is equal to the rate, 5 times the time. Okay, so all you have to do for these problems is to write this as a rate and then substitute it into the problem. All right. Let's do, for this one, this rate is equal to 2.5 miles in 30 minutes, 2.5 miles in 30 or per 30 minutes. I think we should change this into hours. I think that will make more sense. We usually talk about miles per hour, not miles per minute. That's not going to be very many miles if we change it into minutes. So let's go up. So maybe I'll do 2 steps. Okay, so 30 minutes, 60 minutes is an hour. So 2.5 miles would be 5 miles. So if I got 2.5 miles in 30 minutes, then I must go 5 miles in 60 minutes. And this is 1 hour. So this is 5 miles per 1 hour. And then I can write that as D equals 5. Oh, they were both 5. T. When you're doing your big ideas, they will not all be the same answer. That was maybe not a great example. Okay, I know those notes were long. Hopefully you divided it into 2 chunks.